To begin, we're going to use Desmos or graphing calculator, if you have one, to sketch the following functions. These functions are inverses of one another. To begin, we have this red line, and its inverse function is this blue line. Let's see if there's any points that we can see. Okay, we have a point that's 3, 0. We have, oh, this one's 0, 3. I wonder if that keeps going like that. What about this one? -1, -1. Okay, this one is -5, 1. -0.51. So if I go to 1, will I get 0.5? Oh, looks like these x and y values are kind of switching places. Let's try some other ones. X cubed plus 1. And then its inverse function, ooh, has this nice sort of symmetry to it. Okay, this point is 0, 1, and this point is 1, 0. This one is 0, -1, and this is -1, 0. And they're always crossing at a point that the x and y are the exact same. And graphically, they look kind of pretty. They are actually reflections over the line y equals x. So every point on this green graph is the same distance from y equals x as the corresponding reflected point from the purple graph. So the pattern that we saw graphically, the graphs are a reflection over the line y equals x. Okay, and the transformation formula to get from f to g, if I say, hey, here are the points of f, find the points of g, we just need to swap them. So the y becomes the x and the x becomes the y. And that's how we find inverse functions, literally by swapping x and y and solving. So steps for finding the inverse. Rewrite f of x as y, okay? We don't need function notation. And then exchange x and y. You're literally going to swap the places of x and y. Then you'll solve for y. And then at the end, of course, you'll write the inverse notation. F inverse of x, or inverse of f of x. This does not mean 1 over f of x. This is not a wrong side of the fraction bar situation. Okay, this is just a notation. So literally this -1 has no mathematical meaning except to tell you, hey, this is the inverse of the f function. So let's find the inverse. First of all, we want to replace the f of x, or the function notation, with y. If you like to work with y and x instead, that's totally fine. That's what I'm going to do. X minus 3 to the power of 5. Now I've replaced the function notation with y and the input with x. That was just my own thing. That's not part of the inverse. Okay, now the next step is exchange x and y. We're literally going to swap places. So this y is going to go in here, and this x is going to go out here. X equals negative y minus 3 quantity to the power of 5. We need to get y by itself, okay? The first thing I'm going to do is start furthest away from y, and I have a power of 5, and I have this -1 being multiplied in front. So first of all, I want to get this -1 out of the way. So I'm going to divide by -1 on both sides. X divided by -1 is just -x. So you have -x is equal to the quantity y minus 3 squared to the 5th. Now the entire right side is being put to the power of 5. So at this point, we can 5th root. Why could we not 5th root before? Or why is it smarter to 5th root now? Well, this -1 was not being raised to the power of 5. So we take the 5th root of both sides. fifth root of negative x. Fifth root and to the fifth, so you're left with y minus 3. Okay, we're trying to get y by itself, so add 3 on both sides. And I'm going to write y equals the fifth root of negative x plus 3. As far as simplification goes, you should not have a negative under a root, okay? If you do have a negative under like an even root, like a square root or a fourth root, then you end up dealing with imaginary numbers. But if you have a negative under a cube root, an odd root, so 3 is an odd number, cube root or a fifth root, that's simply the cube root of negative 1 times the cube root of x. That is negative 1 times the cube root of x, which makes it look a little bit cleaner because you don't have a negative under that root. You can simplify it, and you should /have to. So y is equal to negative fifth root x plus 3. And our last step is to replace y. Remember, we were not dealing with y at all. We were dealing with g of n. So I will write this as g inverse of n is equal to negative fifth root of the input was n plus 3. And that's the inverse. Let's check from yesterday. If you have a function that has to the power of 5, then you know that your inverse should have a fifth root in it. First step is to replace the function notation with y. Now swap x and y. Y is under this massive fifth root. Now, if everything is being fifth rooted, then I can take everything and put it to the power of 5. And that is what's happening, so that's what I'm going to do here. Take both sides and put it to the power of 5. X to the fifth is equal to, now the root is gone, you still have a fraction, y plus 1 over 2. If you're taking some quantity, y plus 1, and you're dividing by 2, and you want to get that 2 out of the denominator, what do? You times both sides by 2. Okay, 2 over 2 is just 1. So on the left side, you have 2x to the power of 5 is equal to y plus 1. Almost done. Subtract 1 on both sides, and y is equal to 2x to the power of 5 minus 1. Remember to replace that with inverse function notation. The inverse of the f function is equal to 2x to the power of 5 minus 1. You had a fifth root, so it makes sense that your inverse would have something to the power of 5. We will replace this with y equals negative 2 over x minus 2 minus 1. This whole fraction is negative, which means you can apply the negative to the numerator or the denominator, just not both. I would like to apply it to the thing that has less stuff in it, right? I don't want to have to try to remember to distribute. So I'm going to write this as negative 2 over x minus 2. It'll make it just a little bit easier when we solve. Now we will swap y and x. Negative 2 over y minus 2 minus 1. Start furthest away from y and then move in closer. So we're going to add 1 on both sides. X plus 1 is equal to negative 2 divided by y minus 2. Some students prefer cross multiplication. I'm going to put this over 1. Remember, any quantities need to be multiplied together. So this times this, x plus 1, multiplied by y minus 2 is equal to 1 times negative 2. You may say that does not look like an easier equation to solve. Well, it actually is, though, because we've moved the y out from underneath the negative 2. And now we're just going to kind of swap the places of the x plus 1 and the y minus 2. So x plus 1 over x plus 1 is 1. Y minus 2 equals negative 2 over x plus 1. This actually makes sense because 2 is equal to 6 over 3. But if I switch the order that these are in, if I say, oh, no, 3 is equal to 6 over 2, did I change the meaning? Is it still equivalent? I didn't change the meaning. It is still equivalent. And our last step would be to add 2 on both sides. And you end up with y equals negative the fraction 2 x plus 1 plus 2. And this is the inverse of the f function we started with. So we'll put f inverse, the little negative 1 of x, is equal to negative 2 over x plus 1 plus 2. Replace this with y, negative 2 plus cube root 4x over 2. I'm going to use x and y again just to make my life easier. Now swap or exchange x and y, negative 2 plus the cube root of 4y over 2. This entire thing is being divided by 2, so we need to multiply both sides by 2 over 1, or just 2. So you have 2x is equal to the fraction, oh, no longer a fraction, right? 2 over 2 is 1, so 2 plus the cube root of 4y. Start away from the 4y, so we're going to add 2. Add 2, 2x plus 2 equals the cube root of 4y. Almost done. Cube root, how do we get rid of that? We cube it. You do not need to expand to the left side, so you can just write it as a quantity being cubed is equal to 4y. Divide both sides by 4, and you get your inverse. And it was originally g of n. So we'll write g inverse of n is equal to 2n plus 2 quantity cubed over 4. Or you could write it as times 1/4 if that's more comfortable for you. That's finding the inverse.